Hello, welcome to discussion 13 for CS61B. Today we're going to be talking about the first part of graphs as well as LLRBs. So let's get into it. Here are some announcements and let's get into review. So let's start kind of with B trees. So B trees, also referred to as 2-3 trees, which is like one type of B tree, are trees that are kind of similar to binary trees, except for the fact that they are auto-balancing so that you'll never have a spindly tree. Every leaf node in a B tree will always be the same distance from that root node. So you can see here that everything is exactly one away. Every leaf is exactly one away from our root, and this will always be the case for B trees. So in a 2-3 tree, which is a specific type of B tree, each node can have up to 2 items and 3 children. The 2-3 refers to the number of possible children that non-leaf nodes can have. So the minimum is 2 and the maximum is 3. Other forms of B trees, such as 2-4 trees, can have between 2 and 4 children, and therefore up to 3 values in each node. So in this case, we have this node that has 2 items, and because there are 2 items, there have to be 3 children. If your item is less than the smallest item in this node, it will be the left child, and then if your item is in between the values in the node, then you will be the middle child, and if your items are greater than the value of the largest item in that node, then you will be the right node. So when adding to a B tree, you start by adding to the leaf node, and then you push up the excess items up the tree until it follows the rules from the last side. So in this case, we add this 5 and we add it to our leaf node first, but now our leaf node is something called overstuffed because there are too many items in it. We can only have up to 2 items in a 2-3 version of a B tree. So we take this middle node and we push it up to the node above it. So here we have a 3, 5, 7 in this upper node, and again this node is overstuffed because we can't have this many items. Also, you'll notice that we have 4 children, but these 4 children still satisfy our rules that we mentioned earlier in that 1 and 2 are less than 3, 4 is between 3 and 5, 6 is between 5 and 7, and 9 is greater than 7. And then next, we're going to push this 5 node up again to form a new root node that's just 5. And then we have 3 on its left side and 7 on its right. And then we have these children divided amongst those new nodes. And as you can see, the leaf nodes are still all equidistant from that root. Now everything is just 2 away rather than being 1 away. So the problem with B trees is that even though they're very good at what they do, they're really hard to work with in code. Having that sort of variation where sometimes there are 2 children and sometimes there are 3 children and sometimes there's 1 value and sometimes there's 2 values is really bad because it makes it so that they get to check a lot of cases when we're programming. In order to avoid this, what we do is we convert our B tree into something called a left-leaning red-black tree. And these left-leaning red-black trees are essentially binary trees, except with some additional properties which allow them to convert back and forth with a B tree. So in an LLRB, every node that in the B tree version has 2 values gets converted into 2 nodes where the smaller value becomes a child of the larger value. And that value gets coded with a red node to signify that it's actually part of the same node as its parent. So in this case, 3 and 7 are this root node. So 7 becomes the root of our LLRB because it is the larger value. 3 becomes the child of 7, but it's coded with that red node so that the parent, it knows, you know when you're looking at this, and the computer knows that this 3 is actually part of the same node as its parent. The children for these nodes get divided up such that the smallest child, which is 1 and 2, get put as the left-hand children of 3. 4 and 6, which are between 3 and 7, become the right-hand children of 3 because, you know, if you remember from our B tree or BST discussion, this means that it's between 3 and 7. And then our largest node, which in this case is 9, ends up being the largest node on the right of 7. Now, how do we maintain these B-tree properties when we're dealing with a LLRB? So rather than pushing up, we use these 3 operations in order to maintain the same properties. So the first one is rotate left. So LLRB has left leaning in it, which means that all of our red nodes must be in the left side of our root, or of their parent. So for instance, we have B on the right of its parent right now, which is not allowed. So instead, what we're going to do is we are going to do this rotate left operation, which basically takes it and makes B the new parent and A its left-hand child. And we swap the colors here because now A is a child of B. D moves naturally to stay the right child of B, but C goes from being B's left child to being A's right child. The same thing happens with rotate right, except the other direction. And the reason we would use rotate right on an LLRB for a 2-3 tree is to prevent this case where we have these 2 red nodes in a row, because that's not possible, right? If we have 2 red nodes in a row, that effectively means that we have 2 items, like D is part of the same node as B and B is part of the same node as A, which means that there's too many items in this node. So we kind of use both of these operations to fix that. We first rotate right, which will make B the new parent, D the left-hand child, A the right-hand child, and C goes and churns from B's right child to A's left child. And then we use something called a color flip, where we switch the color. Instead of D and C being red, we make A red. And this is essentially the same thing as pushing up, because before we could consider it as D, A, and C are all part of the same overstuffed node, and A is that middle child that then gets pushed up to be part of the same node that B is in at this point. So that's what color flipping does. It's the same thing as pushing up in our B tree. Now switching tracks a little bit, we're going to talk about graphs. So graphs are very similar to trees. They're structures that contain nodes and edges. The big difference from trees is that graphs do not necessarily have to have no cycles. So in a graph, you can totally have multiple ways to get to the same node and things like that. There's no limit on the number of edges, other than the fact that obviously you can't connect the same thing twice. Graphs can be either directed or undirected. So this is an example of an undirected graph. As you can see, there are no arrows, which means that you can go from A to B just as you can go from B to A. It's like a symmetric relationship. On the other hand, in a directed graph, you can only go in one direction. So you can go from A to B, but you can't go from B to A. There are a couple ways to represent these in code, because although this image is really helpful for our human eyes, obviously we can't just insert this image into our computer. So the way we usually represent graphs is we have some sort of representation of what nodes are connected to what other nodes. The first example of this is an adjacency matrix, which is basically a 2D array with true or false values, or 0 and 1 values, that are true if there is a line going from A to B and false otherwise. So in this case, we see that there's a line going from A to B, so we have 1 at that intersection of A and B. So likewise, A to C, there's a 1 right here, etc. You can look at this whole graph and you'll see that only in places where we have this directed edge do we have a 1. If this was an undirected graph, we would use the same exact format, except this matrix would be inherently symmetric, because if you can go to A to B, then in an undirected graph, you can also go from B to A. So it would be mirrored across this x equals y axis right here. I guess we don't have it here, but another way that we also represent graphs is using an adjacency list instead. And in an adjacency list, basically what you do is you have a list of all of the edges that whatever node connects to. That is the other option. There are different reasons to use different ways. If we're a really dense graph, adjacency matrices are faster because arrays are generally faster. If you have a very sparse graph with very few edges, then it's usually better to use an adjacency list because you don't have to have this full massive 2D array. So just like for trees, we can do most of our searches on graphs as well. The only one that we're not capable of doing is in order depth first search, because there is no, unlike binary trees, there is no like left and right node in a graph. However, there is one small thing that we have to change. That thing being that once we've visited a node, we do have to mark it so we don't revisit it. This wasn't a problem in trees because in trees there's only one way to reach each node, so we didn't have to worry about marking it in case you came across it again. However, in this case, it is possible to come across the same node twice. We just got to make sure that we don't accidentally head back down that path, or else we might end up in some sort of loop. So DepthFirst Search goes in order of how far each node is from the starting node. So for these nodes, first A is 0 away from itself, B and C are 1 away from A, F and E are 2 away from A, and D is 3 away from A. And then you see that D points to B, but since we've already visited B, we're not going to revisit it. DepthFirst Search does, again, something very similar to what it does in trees, in that you'll use a stack and you will go down a single path. So for in order DepthFirst Search, you would visit A, and then B, and then E. And then once E has no more children, you go back up, and B has no more children, so you go back up. And then you visit C, and F, and D. But we've already visited B, so we're not going to revisit it. D has no more children, so you go back up. F has no more children, so you go back up. And C has no more children, so you go back up, and you've finished traversing your whole graph. So again, it's very similar to how we do it for trees, with the caveat being that we have to make sure we don't accidentally revisit a node. The last thing we're going to talk about quickly is a topological sort. So a topological sort involves taking a graph that has no cycles and laying it such that all of its edges point in the same direction. So you can think of it as having a prerequisite, every prerequisite for each node physically to the left of that node. This is useful for things such as, in this case, let's say you're trying to figure out what classes that you want to take to graduate, and these are the lists of classes, and obviously you can't take classes in any old order. You do have to have certain prerequisites for most classes. So 170, you need to have taken both 61B and CS70 before you're ready to take 170. So in this case, because there are no cycles and it's a directed graph, we can make a topological sort, and here might be a sample class schedule. Maybe you take 61A the first semester, then 61B, then 61C, then 70, and then you take 170 and 186. Now, of course, there's different ways to do this. Topological sorts are rarely unique. For instance, you might want to take CS70 right after 61A and then take 61B, and that's totally fine because 61B and 70 are completely unrelated. Neither is a prerequisite for the other, so you can do them in any order. Let's talk about the worksheet. So first, convert the following red-black tree into a 2-4 tree, and then let's talk about it. Okay, let's go over it. So the way I personally like to do, first things first, keep in mind that this says 2-4 tree, not 2-3 tree. So this is not a valid LLRB for a 2-3 tree because we do have this node here that is pointing to the right, but it is a valid LLRB for a 2-4 tree because in a 2-4 tree, you can have up to 3 values in each node. That is important to remember. The way I like to do these types of problems is I personally like to draw out what nodes all must go together. So every time I see a red node, I'm like, okay, this must be part of its parent. So I'm going to circle that. And likewise, I'm going to circle down here both of these. And these are going to be our multi-value nodes in our 2-4 tree. The only arrows that we really have to represent in our 2-4 tree are the ones that are not encircled completely in one of these values. So in this case, you see that we have 12, 25, and 31 in one node. We have 8 by itself, and this arrow out here connecting those two. 14 and 19 are also one node connected by this arrow right here. 27 is in its own node connected by this arrow right here. And then 33 and 46 are in their own node connected by this arrow right here. And we get this correct 2-4 tree just like that. Next, I want you to insert 13 and 17 into this resulting 2-4 tree. I'll give you a chance to think about it. Okay, let's go over it. So first, we're going to add that 13 to this node right here because 13 is between 12 and 25, and that results in this node having 3 values, which is totally fine because like we talked about, this is a 2-4 tree, so you can have up to 3 values per node. Next, we're going to add the 17, which again goes into that same node because 12 and 25, 17 is between 12 and 25, and now we have too many values. Now this is overstuffed. So we're going to take this 14 and we're going to push it up. This is really a matter of convention. As long as you push up the same value every time, it doesn't matter whether you choose the center left or the center right. I like pushing up the center left. If we ever ask you to do this in an exam, for instance, we will tell you what convention to use. So we push up this 14, but now this tree has, this node has 4 values and 5 children, which is too many for a 2-4 tree. So what we're gonna do is we're gonna push up again. This 14 goes up one more time. And now this 14 is the root, the 12 is this child, the 25 and 31 are on this side, and those 5 children get divided up proportionally based on how many children each node should have, right? Because if a node has 2 values, then it has to have 3 children, and if a node has 1 value, it has to have 2 children. Okay, so now we're gonna see how to convert our resulting 2-4 tree back into a valid LLRB. I'll give you a chance to think about it. Okay, let's go over it. So this is going to be the valid result, and so the reason is because 14 is in that node all by itself, and then 12 is by itself as well, with 18 and 13 again by themselves. So this is a pretty basic normal BST looking side. On the other side, however, 25 and 31 were together in that node, so we're going to split them up and have 25 be the child of 31 and then label it as a red node. 25's left children are going to be that node with 17 and 19 in it, so again, we're going to have 19 be that parent and 17 be the child. 27 is between 25 and 31, so we're just going to put it as the right child of 25. And then 46 and 33 were greater than 31, so we're going to have those be on the right of 31, with 46 being the parent and 33 being the red child. Okay, this is kind of more of a conceptual question. So given a 2-4 tree with n keys, how can you obtain the keys in sorted order in O of n time? I'll give you a chance to think about it. Okay, let's go over it. So in this case, we're just going to generalize an in-order traversal to apply to B trees or 2-4 trees. So we're going to traverse the left and then emit the first key of the node, traverse the second child, emit the second key of the node, etc. Let me show you what that looks like on a 2-4 tree. So it's going to result in some kind of an interesting kind of wave pattern. So we're going to start, like for instance, if we wanted to traverse the subtree, we would have to emit these 2 values and then 25 and then emit this value and then 31 and then this value. So it's kind of the same as an in-order traversal except with a little bit more nuance because we now have multiple values per node and they aren't going to all be emitted at the same time. Okay, last question about 2-4 trees. If a 2-4 tree has a depth of h, what is the maximum number of comparisons done in the corresponding LLRB to find a certain key? Okay, so in this case, the maximum number of comparisons is going to be 2h comparisons. So the maximum number is going to happen if you're going down that leftmost track, and every single node on the B tree, on the 2-4 tree, has a max of, has the full number of values, right? And in that case, you'll compare to that middle thing, and then if it's less than, you're going to compare also to that node that is to the left of it. And so that is basically 2 comparisons per node, and there are the height of the tree is h, so that means that there's h trees on that, h nodes on that path from root to leaf. So the total number of comparisons is 2h. Okay, let's do some graph stuff. So let's represent this graph with both an adjacency list and a matrix representation. I'll give you a chance to try it out. Okay, let's go over it. So first, let's do this adjacency list. So in this case, we are going to see that A is pointing at B, E, and F, And so we have B, E, and F on A's adjacency list. For B, we see that B is only pointing at D, so that's all that's going to be on B's adjacency list. C has no outgoing arrows at all, so its adjacency list is going to have nothing in it. D is pointing at both C and E. E is pointing at nothing, again, no outgoing arrows, and F is just pointing at E. So that's our total adjacency list. Our adjacency matrix representation is we are going to do, again, see that A is not pointing at itself, A is pointing at B, A is pointing at E, and A is pointing at F. So those are all the ones in A's category. Likewise, B is only pointing at D, so everything else is zeros. C isn't pointing at anything, so this whole line is going to have only zeros. D is pointing at C and E, so those two are going to be ones. E is pointing at nothing like C is, so it's all going to be zeros. And F is just pointing at E. Now let's run DFS pre-order, DFS post-order, and BFS on the graph starting from node A. I'll give you a chance to try it out. Okay, let's go over it. So for DFS pre-order, we're going to start with A, and so that's our first item, and then we're going to go to B, and B is our second item, and now we're going to continue going down this path to D. That's our next item, and then to C. And so now that C has no more children, let's go back to D, and D has another child, so then now we can add E to our list. E is not pointing at anything, so we can go back to D. We visited both of D's children, so we're going to go back to B. And likewise, B has no more children, so we're going back to A. A is pointing at E too, but we've already visited it, so there's no reason to re-add it to our list. So the only thing left is F. And likewise, E has already been visited, so F has no more unvisited children, so we're going to go back to A, and we're done. So that's how we get this order, A, B, D, C, E, F. For DFS post order, we do the same traversal, except we only add things to the list once we've seen them. So, or once we've seen all of their children. So we're going to start at A, but we're not going to add it to the list until we visited all of A's children. Likewise with B and D. And now we're at C, and C is the first node that we visit that doesn't have any children, so C is going to be the first item on our list. Now we're going to go back up one. Now D still has a child that is unvisited, so we have to go there first, which is E. E has no children, so we can add E to our list, and then we can go back up to D. Now that D is done, we're going to add that to our list, go up to B, and likewise B has no more children, so we can add B to our list. A still has one unvisited child, that is F, so we're going to go there. F has a child, but E has already been added to our traversal list, so there's no need to re-add it. So we're going to add F, and now we're finally up to A, and all of A's children have been visited, so we can add A to our list. So this is the DFS post order. One thing to note is that a quick way to get a valid topological sort is to run post order and then reverse the result. So in the case that there are no cycles, such as this graph, A, F, B, D, E, C is actually a valid topological sort for the graph. There are others that are also valid, but this is just one option. And for breadth first search, we're going to do normal breadth first search. So we're going to start with A because A is 0 away from itself. Now we're going to go to B because B is alphabetically first and add that. And then E, which is also 1 away, add that. Same with F. And now we're going to look at everything that's 2 away. So in that case, that's just D because E has already been added to our list. So we're going to add D. And then we're going to look at everything 3 away, which is just C, and add that. So we get A, B, E, F, D, C. Okay, let's do a topological sort. So I talked about how you can get a valid topological sort. Why don't you guys try filling this out, and then we'll go over it together. Okay, so let's go over it. So like we talked about before, if we reverse that topological sort, that's one option. This is another option. In this case, A goes first because a lot of these things depend on A. And then, it looks like it's missing an arrow going from A to F, which there should be. Sorry about that. But basically, this is one valid topological sort if there was an arrow from A to F. But broadly, there are other ways that you could restructure this. For instance, F is not dependent on B, D, or C. So F could happen anywhere in between these, and all of that would be valid. So it isn't unique, but it is one option. And that brings us to the end of this discussion. Thank you guys for coming, and I'll see you guys next week. Bye.